I guess at last I could work it out that you could see the result of the quiz with correct answer, yeah? So it's working now. Okay, let's continue. What we talked before, we talked about Boolean algebra and also started about looking at the gates. We talked about theorems and application and gates. So let's continue. We go to gates and to show you how to realize a circuit based on the function that we have and using truth table to do that. Just a review. What were the basic gates? They were not, and, or. So we had not is this. We had or, which has two inputs, one output, and. And the truth table of these things we have seen before. And is one only if and only one, both if and only if both inputs are one, or is zero if and only if both inputs are zero, and not is the not. So if the input is 1, the output is 0. If the input is 0, the output is on. Now we introduce another gate, NAND gate. Have you heard of that? NAND gate. Where did you hear? In any course or?
We were fiddling around in the lab yesterday.
Oh, okay. Oh, good. Perfect. So the lab. NAND gate. NAND gate, as we can guess from its name, it is an AND gate plus NOT. It is not of an AND gate. AND gate followed by a NOT, by an inverter. So if this is an AND gate, which we have already seen, and then we put another NOT after that, then we have a NAND gate. To show it, we can just use, instead of writing the NOT every time with this, we just put the circle at the output of the AND gate. So this is the NAND gate. It is an AND with a circle at the end. This circle always shows inverter. And usually, actually, it was the real inverter. But why we draw it like that? Because we cannot leave a circle in the space. So we put a triangle before that. Otherwise, this would be enough. This is the NOT. But this is NAND gate. So NAND is what? Is ANDing the input and inverting the whole thing. Okay? This is the NAND gate. You remember De Morgan's rule? We talked about De Morgan's rule. So when you negate an AND, it becomes OR with the negating of the inputs. So A, B, NOT, which is an AND, equals to A NOT or B NOT. They are the same. So this is the NAND. A NOT or B NOT is the NAND of A and B. Okay? And this is the truth table. Let's see it together. When A and B are 0, the result of AND is 0. So the result of NAND is 1. Again, when A 0, B 1, AND becomes 0. NAND becomes 1 because it is negated. 1, 0, AND is 0, so NAND is 1. 1, 1, AND is 1, but NAND is 0. So you could see that NAND has 3 1s, 1 0. When it is 1 1, it is 0. Otherwise, it is 1. The next one is NOR gate. NOR gate, again, as you could understand from its name, it is an OR gate plus a NOT, an inverter. So OR gate followed by an inverter. So you have OR gate, OR is like that, and then we put a NOT gate after that. We can show it like that. Again, this could be removed and just the circle would be placed here. So this is the NOR gate. NOR is OR with NOT. So NOR which has been inverted. So if we want to use De Morgan's rule, it becomes OR becomes and the inputs are negated. So it becomes A naught and B naught. So this is NOR. And again, we can have the truth table for that. So the truth table, again, 0, 0, OR is 0, so the NOR is 1. 0, 1, OR is 1, so the NOR is 0. 1, 0, OR is 1, the NOR is 0. 1, 1, again, OR is 1, so NOR is 0. Negation the OR, inverting the OR, yeah. So it has 1, 1, and 3 zeros in the truth table. This is NOR gate. It is good to say that NAND and NOR gate are a little more special. What do I mean by that? Let's say about them. You can use only NAND gate to implement everything. We said before, the basic gates are AND or NOT. So you can implement every Boolean expression with these three gates, NOT, AND, OR, of course, because you either invert something or either OR it or either AND it. Now I am saying that you could implement everything with NAND, just one gate, NAND, one type of gates, not one gate. If I want to show you that, I just show you how could you implement AND, OR, and NOT with just NAND, then you could do everything else. Okay. So implement either NAND or NOR, both of them. You can use NOR gate to implement everything. You can use NAND gate to implement everything. They are said to be functionally complete because of this property that you can use it to build everything. We say they are functionally complete. Both NAND and NOR gates, in design, they are variable because first, they implement everything, and second, this is very important, which I could explain for you maybe later if we have time, because it goes to the implementation to the transistor level. I told you we have at the bottom we have transistor, then in the next abstraction level we have gates. The next abstraction level we have RT, register transfer level, and at the bottom, at the top we have system level. I've told you before that. So if I want to tell you why the digital circuit and the design with NAND is very good, is more optimized, I should give you the inside design of NAND based on transistors. Just to know, just for you to know, I could say that a NAND gate consists of 4 transistors. But, for example, an AND gate has 6 transistors. NAND 4. NOR gate has 4 transistors. NAND and NOR are very similar. They are just dual of each other almost. But OR gate has 6 transistors. Inverter NOT has 2 transistors. So inverter is very simple, just has 2 transistors in CMOS. I didn't tell you about CMOS, no? No, I didn't. It was the other class. So in CMOS, Inverter has 2 transistors, then NAND has 4 transistors, then AND, for example, has 6 transistors. So if we have an expression, a Boolean function, when we want to implement it on a digital, as a digital circuit, it will be very good if we could build it using NAND gate. NAND is very good for digital design. And also, they are typically faster. This is also important. NAND is faster than AND. Because again, if I want to explain you why, I have to show you the transistor level of NAND and AND. In NAND, from the input to reach the output, we pass 1 transistor, but in AND, from the input to output, we pass 2 transistors. So it has 2 delays, 2 level delays. But NAND has 1, so NAND is faster. I don't go through the detail of that because I am sure that you don't like it much, but if we have time, I might tell you, because it is good that you know what's happening inside. Oh, okay, I find out what is NAND, what is AND, what is not. But what is really inside the circuit, below that, in the next? It is good to know, but for the time being, we pass. Maybe later I will tell you more about that. Yes, please.
What do you mean by functionally?
It means that you could build everything, every function based on this gate.
Just one?
Just NAND gate. Just one type, not one gate. Just one type. If I give you a NAND gate, I put you 1,000 NAND gates here, then you could use it to build any circuit device. But you cannot do this with AND.
But instead of something like
NOR the same. NAND and NOR, they are both functionally complete, but AND no. With AND gate, you cannot build, for example, OR. With AND, you cannot build OR. But with NAND and NOR, we can. I will show you right now. How could you build OR gate with a NAND gate? How could you build an AND gate with a NOR gate? So these are 2 important gates, and it is mainly due to its architecture, its implementation by transistors, which we don't go through them like right now. Maybe later. So they are functionally complete. For example, this is a NOT gate. If you connect both inputs of the NAND gate, then you have a NOT. Do you agree? Let's see. Here, what did we have? A as input, A as another input. So this is A and A NOT, NAND. NAND is this. A and A is identity. A and A is A. So we have not A. Okay? We just used a NAND to build a NOT. Okay? So let's go to the next one. AND gate. AND again is easy because we had built NOT, we use NAND and then we use a NOT to make it AND. Here you see, here up to this point we have NAND. It means that we have AND of A and B NOT. This is NAND. Now if we NOT it again, the invert of invert, you know that the invert of invert is this. So using NAND, using just NAND, we could build AND. Okay? Now OR. How to do OR? How to do OR? You know, because when we were talking about NAND, I told you NAND is AB NOT. And if we use De Morgan, it is A naught plus B naught. So you could see here an OR. from this you can guess how could you implement OR. If you invert both inputs first and then NAND it, then you have an OR. And NAND is a NOR with negated inputs. Okay, so if you start with A and B, then both of them inverted. So here you have A naught and B naught. Then A naught and B naught NAND. So the result would be A plus B.
For the first one, like AB negation.
Okay.
Like with AB negation, the last step. So how we get like inputs?
You mean the OR one, yeah? Okay. So this is not. Do you agree? I show you here. This is not gate. And this is also not. So we have A not here. Okay? And we have B not here. A naught and B naught, let's NAND it. So NAND A naught and B naught. A naught and NAND B naught. NAND means and then not. Okay? This is NAND. A naught and B naught, not. So it is NAND. Okay? So what is this? Using De Morgan's. De Morgan says AND becomes OR. This input inverted, A naught inverted, so A naught inverted, plus this input inverted. Okay? And invert of A naught is A. A naught not is A, and B naught not is B. So just using 3 NAND gates, we could build an OR gate. Using 2 NAND gates, we could build AND gate, and using 1 NAND gate, we could build NOT gate. Okay, so they are fine. And you could do the same thing with NOR because they are dual of each other. For NOR, if you connect both inputs together, then you get a NOT. If you do like that, you get an OR. And if you do the same thing here, you get an AND with NOR. The other gate that I would like to present to you is XOR, exclusive OR. From the name, what do you suggest? What do you understand? Exclusive OR.
It means that so long as the two inputs are the same, we're going to get a false return.
Yeah, because it is exclusive OR, exclusively, either this or that, not both of them. In the regular OR, if A is 1 or B is 1 or both of them are 1, we get 1, you get true. But in exclusive OR, it says that it should be only one of them. Either A is 1 or B is 1, not both of them. If both of them are 1, then we get false. So this is exclusive OR or XOR. We say XOR. So the symbol would be like that. It is like OR and with a line here, with a curve here. So this is exclusive OR. And exclusive OR assert their output when exactly one of the inputs are 1, not both 0. So just one of them. And we use this symbol for exclusive OR. When you write A, it means exclusive OR. And the truth table, let's have the truth table. This is the truth table. When both of them are 0 or 1, the result is 0. But if either one is 1 or the other is 0, then the result will be 1. So this is the truth table of XOR. The next one is XNOR. You could guess that it is XOR and not of XOR. And it means that if both of them are 1 or 0, then the result is 1. If one of them, if they are different, then it is 0. Complements of XOR. So again, here you see we put a circle at the output of XOR. So this is XNOR gate. And the symbol is this. So you say A, this is XNOR, and the truth table with that. If both of them are the same, then the result is 1. If they are different, then the result is 0. Now that we see the gates, now go to the functions. You have already seen lots of functions. For example, this one. A function of x, y, z. We have three inputs, x, y, z, and the output, the result, the function would be x, y prime plus z, x prime. Usually in writing we use prime, single quote. It's easier to write because in writing I cannot write in PowerPoint this. It's not easy. So I put prime, that would be easier. And I mean by prime, by single quote, I mean bar, not. So this is a function, x, y prime plus z, x prime. It means that you invert y and then AND it with x. You invert x and then AND it with z, and then OR the result of these two together. Because we have talked about the precedence. The precedence first is not, then AND, then OR. So first you should calculate the not, the negation, then you should see the ANDs, and then you should see the OR. If I want to write it as with parentheses, it would be like that. Y should be negated, then should be AND with X, and then the same thing here, X should be negated. Oh, sorry, this parenthesis should be here, not that. And then X negated, then AND with Z, and then these two OR together. This is the same as that one, and you see how ugly is this one, so that one is much better. But we know that the precedence is invert, then AND, then OR. Okay, let's look at this. Function of x, y, z is x, y prime x, y prime plus z, x prime. F is the name of the function. F, we call it F. You could call it anything. There are terms in the functions. Now we have two terms here. One term is xy prime, the other is zx prime. So we use the products, the ANDs, as a term. Their term is an implementation with a gate. In this example, f has two terms, xy prime and zx prime. X and y and z are the input variables, and each one of them is a Boolean function, is a Boolean variable, is a digital signal, either 0 or 1, either true or false. And if we go to the circuit, either 0 volt or 5 volt, high volt or low volt. A literal is the elements that inside the terms. For example, here we have x, y prime, z, x prime. So these are our literals here. We have 4 literals here. Okay. So just some kind of terminology. Now, I talked about this. The precedence is first parentheses, then not, then and, then or. So this means that first you have to calculate this parenthesis. Yes.
I have a question with the last one.
Okay.
With terms, wouldn't both terms create a new term because of the addition?
Yeah, we assumed, we set this rule that the terms are, you have some kind of sum of products or product of sums. The terms would be the inside. So here, since we have sum of products, each product is a term. If I've written this something like that, x plus z and y plus z prime and z plus t, so on, then these were terms. Here we call these things terms. It's just a terminology. No, I don't think we can use that, but we will make it a standard forms, and then we will talk about the standard form. Here, for this function, we first should calculate the parentheses. When we go inside the parentheses, we have x plus y prime. So we first calculate the naught of y, and then the result would be ORed with x. So this is the parenthesis. Then you see we have and here, or here, prime here. So again, we then calculate this prime first. Then we go to and. We don't, for example, here, you don't OR z with x prime and then and the result with the parenthesis. No, we should calculate this NAND first. This is calculated first, and then ORed with x prime. So these are the precedents. Yeah, if you want to write it in the parentheses, it will be something like that, and it is very complicated and ugly. So that will be easy, but we set this rule that the precedence is like that. It is something like in the normal algebra also. In normal algebra, when you write x plus y z in normal operations, it means that you just first multiply y by z and then add to x. This is almost the same. Truth table. We have talked about truth table, that the truth table is something that shows you the truth and falseness of an expression for all possible inputs. For example, if we have a function with 3 variables, 3 inputs, then it means that we have 8 possible states, 8 possible conditions, and they would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If you convert it to decimal, they represent the numbers from 0 to 7. Okay. Inputs are listed in binary order. This is good because then we don't get confused. You just put an order so you know that you have covered everything. If you don't have this order, then you might lose some inputs. So for example, this one, f x y z is x plus y prime, then and with z plus x prime. So let's see what happens. Okay, let's calculate ourselves. So let's draw the truth table. The truth table would have the inputs would be x, y, and z. They are the inputs. And then we have the output are function. But I know in our literals, I have y prime and x prime. So let me also have y prime and x prime here. When you when you do more practice, then you don't need to write this. You just do it in your mind. But now I am writing, because I have the literal of y prime and also x prime, I also include those in my truth table. And then we have, let's say, x plus y prime. So, I don't have a space here. X plus y prime here. And then I have x plus y prime times z. I don't have, I draw it bad. So how could I do that? I don't. So this one, I call it expression A here. I can't. Okay, let's do them in our mind. So here I put f. Let's see if we can do it in mind. Okay, x, y, z, all the possible inputs, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If you look at the numbers, they are from 0 to 7. From 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay. And y prime is not of y. So y is 0, 0, 1, 1. So y prime is 1, 1, 0, 0, 1, 1, 0, 0. And x prime is not of x. So x prime is 1, 1, 1, 1, 0, 0, 0, 0. And then we have x plus y prime. So we have to do it in mind. X plus y prime. X plus y prime means these two together. Instead of doing in mind, let me write it at this side. X plus y prime here. X 0, y prime y. So it is 1. Or of 0 and 1. Again 0, 1. So it is 1. Let me show you. Okay. 0, 0. Here you see x is 0, y prime is 0, so the result is 0. X plus y prime, again 0, 0, 0. 1, 1. 1, both of them are 1, so the all would be 1. Again 1, 1 is 1. 1, 0, 0, 1. So again all would be 1. 1, 0, 1. So this is x plus y prime. What do we have? Then we have to AND it with z. So now we have to AND this with z. This operation AND with z. I call it A. So what is A? This one AND with this one. 1 and 0 is 0. 1 and z is 1. 0, 0 is 0. You know, I am looking at the column, first column, and 1, 2, 3, fourth column. So 0, 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 are 1. 1 and 0 is 0. 1 and 1 is 1. So we have now this as this. Plus x prime. So we have to orient with x prime. Where is x prime? Let me show you here. Highlighter. So we have now this column with x prime, with this. So now we have to OR these two together. So first line, 0 and 1 would be pen, and maybe now it's good to write it in blue. Okay. So this is the function, the final output. And we are ORing these two columns, the highlighted one. 0 and 1 is 1. 1 and 1 is 1. 0 and 1 is 1. 0 and 1 is 1. 0 and 0 is 0. 1 and 0 is 1. 0 and 0 is 0, 1 and 0 is and or and 1 and 1 or 0 is 1. So you see this is the 1 and 1 is 1. 1, 2, 3, 4, 5, 6, 7, 8. 8 possible conditions, and 6 of them are 1, 2 of them are 0. So this is the truth table of that function. If you look at this truth table, it is the same as you have seen that function. They represent each other. That function, this truth table. So again, it is the one. Did we do it correctly? Oh yeah, it is good. 1, 1, 1, 1, 0, 1, 0, 1. Okay, so we have done it right. I was afraid that we might have had mistakes. So this is the truth table. The last result is here. I can now erase all of my writing, so you could see the function. 6 ones and 2 zeros was the result of this function. So let's now go from the circuit to from this to gate. We want to implement this. So this one was from function to truth table. Now we go from function to gate. Let's say this one. This one is a function. What would be the equivalence of realization with gates? Okay, let's do it. We have x, y, and z. And I see that we have x prime also, so I use a NOT gate just here to have x prime also. And then we have y and z. So I have an AND gate here, ANDing y and z. And then we have the result of this AND ORed with x prime. So this is x prime, and they have to be ORed. This is the realization of this function. This is f. These are x, y, z. Okay? You could see that how it works. For example, if you put 0, 0, 0, the first row of truth table, then here we have 0. So let me change the color. So 0 is, we have 0 here. So 0 gets 1 here. So we have 0 here, 0 here, 0 and 0 is 0. 1 comes here, 1 or 0 is 1. So you could use this gate implementation to calculate the rows of the truth table. And you can go for all of the 8 possible conditions. This is the result that we had. Z and Y and X not ORed with them. This is the same thing that we have drawn. Another one. Here, I could have implemented this with 3 input AND gates, because if you see here, we have 3 signals AND together. So I do it first, and then I just use 2 input gates. So first, if I had 3 input gates, so x, y, z, x, y, z. I have z prime, so I will use a NOT to generate z prime. I have y prime, so I will generate NOT also. I have x prime also. So we have all of the literals here, x prime here. Then we have x, y, z prime. So x, y, z prime. They are AND together, AND. So this is the first one. Then we have x, y prime, z. X, where is x? X is here. So let me use another color. So this is x, and then I have y prime, this is y prime, and we have z, this is z. Or I can use this one. X, y prime, z. So they are AND with each other. Then we have x prime, y prime, x prime. So I use another color for the next term. X prime, and y prime. Y prime is this one. And they are ANDed together. So we have these three terms. Now, all of these three are ORed together. So we have a OR gate with three inputs. Which color do I use? Green. So we have an OR gate with three inputs. This one, and this one. So this is the implementation of our function, but with three input gates. You have three input gates. We know everything goes to transistors. If with transistors you can build three input gates, okay, good, use it. If not, I know that we can build two input gates, then use two input gates. As an example, as a problem, I ask you now to think of two input gates. Let's build it together with two input gates. I wish I could just erase this part. Okay, it seems that I can. Good. Okay, again, for the literals, I have x, x prime, y prime, z, z prime. And now let's go it 2 by 2 because our gates are two inputs. Okay. For the first one, x, y prime, and z. Oh, it is x, y prime. So we had a law, associative law, that it says that if you want to do x, y, z, you could do it first x, y, and then AND it with z. So we will do this. We will use this rule. X, y, z prime. X, y, ANDed together. So we have x, y. Now it should be ANDed with z prime. So with z prime. So we just use two input AND gate to generate this. For the next one, for the yellow one, x, y prime, z. X is here, y prime is here, so I AND them together, and then I have to AND it with z. Now could you see? Yeah, okay. So I have yellow one, x, y prime, z. And now let's go to the next one, which I make it blue. The next one is x prime. Oh, it is already two inputs, so it's easy. X prime, y prime, ANDed together. So we have these three. Now we have to OR them together. Again, our OR has two inputs. So let's do them one by one, and 2 by 2. This ORed. And then the result will be ORed with this one. So this would be the implementation of our function using only two input gates. Okay? Yes?
Do we have to memorize the table of the nodes?
Yeah, almost. Yeah, it is not just memorizing. You mean, for example, x, y, z equals to x, y, z. Yeah, you should know that.
Yes.
So all of them are like that. Which one is hard? X times x is what? X. Okay. These are the rules. Maybe the most difficult one was De Morgan's. x plus y bar is, this is the most difficult one. What is that result? X bar and y bar. This is maybe the thing that you should memorize. Okay, so this is the one that we have created. You see, just 2 input gates, and they go 2 by 2, and then the result would be f. This is the same that as we draw in the previous slide. Okay. Another example. There are, okay, again 2 input AND gates. I guess you you know how to do that, but so let's do it fast maybe. Yeah, this is the result. You see, x plus y prime, x or y prime. So this is x plus y prime. Then we have to AND it with z. So we have z, AND it with z. So here we have x plus y prime and z. Then we have to OR it with x prime. So x get negated, prime, inverted, and then they are ORed together. So this would be the result. Okay? Now, if you have a circuit, a realization, then how do you find out the Boolean expression? So if you look at this, let me use this one. Oh, that isn't hard. You start from here y, then it is y prime here, then you have x, so it is x plus y prime. Okay. So the Boolean expression, but it might be not simplified. We could use it from the truth table also. This is the new things that I am telling you. You know, you have a truth table of a function. For example, this function, f1. f1 has 2 zeros here and 6 1 here. What would be the Boolean expression of this function? How could you find out? Yes, please. Tell me something that I do for you. How could we find out what is this? For example, is this one x y prime plus y x prime something? What is this? How could we find out what is f1? What do you suggest? Okay, let me start from a simple one. Then maybe you could tell me how to calculate this one. Let me give you a very simple truth table with 2 variables. So x, y, and f. Yes? Okay. Very good. Perfect. And what would be ORed? For example, if this is the 1. So you are saying that we should OR these together. Okay. And what would this? What? Perfect. Very good. Exactly. Very good. What was your name? I forgot. Chloe. Yeah, Chloe. Yeah. I told you that I don't memorize at one session. Maybe I do learn a little. Okay, so you see, Chloe was just right. So to reach to her point, let me start with a simple and then go there. Let's put a function f, whatever you suggest. Okay, what do I put for function? Tell me 0, 1, 0, 0. Tell me something. 0, then 1, 0, 1. Okay, so this is a function. So 0, 1, 1, 0. This is the truth table of that function. If you look at this, then there are 2 zeros and 2 1s. You know, from the truth table of AND, a truth table of AND shows you 0, 0, 0, 1. AND gets only 1, 1, and the rest is 0. And this 1 corresponds to x and y. So this f is x and y. Do you agree? This f is x and y. This is the truth table of AND. Okay. If I make the function like that, this is 0, this is 1. So what would be the function of f? So here again it has only 1, 1, 3 zeros. So it means that it is an AND. But what would be the inputs? Negation of y or 1. Which one is 0? This one. So negate y and x. Perfect. X and y not. Do you agree? So this function is x, y not. So if I have a function, let's go to function of you suggested. What was your name? Sorry. Chris. Okay, Chris. So this one, if I make it is like this. Your function, I make it two functions. Let's say f consists of f1 and f2. For f1, I put 0, 1, 0, 0. For f2, I put 0, 0, 0, 1. Do you agree that f is the OR of f1 and f2? f1 and f2? Because f is 1 only in this and this position. f1 is 1 here, 1 here. So if we OR them together, then we have f. Okay? And based on what we told you here in the AND gate, what is f1? This is only 1, 1 here. 1 here. And 1 should be, let me bring another color. Okay, let's highlight it. So here we have 1 here. 1. We have 1 here. The rest is 0. This one corresponds to x being 0, y being 1. So if I want to make it an AND, what should I put? You told me at that time. X and not y? No. Now x is 0. Negation x and y. Perfect. So f1 is negate x bar here, x bar with y and y. And f2, what is f2? Tell me together. Tell me. X and y. Yeah, because both of them are here and this is x and y. And I told you f is OR of f1 and f2. So f is, let me write it in black. F is x bar y or xy. And how did we find out? We looked at the, now I clear everything, just this part. So I clear this. Now you get practice, and then you see f has 2 ones. F has 2 ones, this one and this one. This one corresponds to x naught y. This one corresponds to xy. So the result would be xy plus x naught y. Yes? Okay. Now Chloe suggested this before for 3 inputs. If we look at the input, if we look at the truth table here, we have these ones. These ones. This one corresponds to an AND of what? 0, 1, 0. So it is x naught and b, a naught, sorry, a naught. A naught, b, and c naught. Very good. So this is this one. And then we have this one. This one corresponds to a naught, b, c. Then we have this one. A, this is A, B naught, C naught. Then we have this one. A, B naught, C. Then we have this one. A, B, C naught. And the last one is A, B, C. So from the truth table, we found out the Boolean expression of f. But I have written here unsimplified. You might be able to simplify this. Let's do a little on that. For example, you see here we have A naught B C, A naught B C naught, A naught B C. I can factor A naught B and it becomes like that. So let me write it like that. So these two together would be A naught B parentheses C naught plus C. And C naught plus C is 1. So it is A naught B. Instead of three input gates, we have 2 input gates. Very simple, very simplified. We can do more simplification. We can do more. But just to start, it is a very good start. Because when we saw this truth table, how could we find out what function does it represent? So this is a good start. We start with this, and then we try to simplify. Why do we want to simplify? Easier. Gates, less gates. So less gates, less wires to connect them. And so it is cheaper. It is faster. It is less heat generated by the gates if you make them less. So it's good to simplify. And ideally, if we could have time, and I explained for you, NAND is the best. More simplification means to make them more NAND gates. Right now, we didn't care. We just put not and or. So this is the basic gates. It's okay for now. But at the final optimization, it will be good if we could make them NAND gates. And even NAND is better than NOR. I don't go through the detail right now. Very good. So this is what we have implemented. Sometimes it is good that we use, here we have 2 zeros and 6 ones. So when we made it, it became 6 input terms, 6 terms. But if you look at zeros now, we might be able to do it very better. So instead of making F1, I make F naught, F1 naught, F1 naught. The same thing that we have explained before. So F naught would be 1, 1, 0, 0, 0, 0, 0, 0. So F naught, F1 naught is again the same thing. We look at the ones, and here we have 1. And this one corresponds to A naught, B naught, C naught. So it is A naught, B naught, C naught, plus. And we have another one here, which corresponds to A naught, B naught, C. A naught, B naught, C. Oh yeah, you just simplified it. It will be A naught, B naught. Very simple. So the whole thing is that we have seen here with 6 3 input terms, it just become one term, A naught, B naught. But we go through them, how we could do that, how could we simplify that. Now we are using ad hoc solution. You think, you look at them, okay, I can factor A naught, B naught. You see something else. You see, okay, why not using zeros instead of ones? These are ad hoc methods. But we have to find a systematic method that you could start and reach to the most simplified solution. So here, this is F1 naught. Okay, do you have questions over there? Yes, sir. Questions? You could share it with us. It would be very good to know everything. So this is F naught. If you want F, then you knot it. Knot of F naught is F. So you knot it. A naught, B naught, C naught plus A naught, B naught, C naught. Okay? And using De Morgan's, OR becomes and becomes OR. So knot of this would be A plus B plus C and knot of this A plus B plus C naught. So this would be F. But here we have terms of OR. There we have terms of ANDs. Okay? Here we have terms of ANDs. Here we have, just pay attention to this and then we go. Here we have sum of products, SOP. Here we have products of sum, POS. We will talk about SOP and POS in the next lecture. So I guess we will see you on Tuesday. Okay? Have a good weekend, long weekend. Monday is the